Good morning. I'm very happy to be here. Very happy to talk about energy efficiency. My background is system architecture and networking. But also at Juniper right now, I also lead a team that does Silicon Photonics, which is a team actually started by John Bowers. And it was acquired as part of Juniper's expansion strategy. So I'm not an optics expert necessarily, but I'm trying to play one on TV nowadays because I have the Silicon Photonics team. I got introduced to Silicon Photonics originally in Intel when John Bowers had a joint project with one of my colleagues at Intel when they started originally Silicon Photonics. So very happy to talk about energy efficiency needs in the data center. Especially, I think I'll talk about the aspects of system architecture and how they impact energy efficiency. Let's see. Why am I not advancing my screen? So I think one of the things I want to start out by giving the context is that the unstoppable demand for broadband traffic. We are all familiar with consumers on the left-hand side you see here. The broadband demand has been growing, right? Interestingly, the next 1.5 billion users in developing countries are likely to be mobile only. You see that in countries like India, where people just have mobile phone. They don't have necessarily broadband connectivity to home. But what that fuels is the front haul and back haul capacity for broadband. And that's why the broadband capacity that operators and service providers have to provide is increasing a lot. At the same time, people's expectations of the kind of speed they want to get across both fixed networks as well as mobile networks is increasing. People are expecting to see 2 gigabit per second kind of speeds, right? And due to that, IP traffic has been growing very fast, 3x growth in 4 years alone. And mobile data traffic is even more, and all of that is mostly fueled by video streaming, and which is extremely bandwidth intensive. Now, we have new applications like augmented reality, virtual reality, cloud gaming that people are doing more and more rather than using Xbox at home. That also has a huge implications for bandwidth, and that's what is fueling the need for larger and larger data centers, sometimes closer to the consumers. At the same time, enterprises are going through a massive transformation, so-called digital transformation, where they're moving their workloads to multiple public clouds. More and more, it's a very well-known thing that people are not using single public cloud or just being on-prem. Depending on the workload, the kind of data they need to access or store, they use public cloud or some cases on-prem data centers because of regulatory concerns, GDPR kind of data sovereignty concerns, and so on. We have been leading at Juniper efforts to get people to AI-driven enterprise. What that means is that for campus and branch networks and other connectivity like SD-WAN without using dedicated connectivity, use internet for connectivity, how to provide AI ML-based engines which are there to do self-diagnosis based on all the data you can derive from the users. And for example, if you have Wi-Fi network, every enterprise has a Wi-Fi network. The technology we acquired from Mist.ai allows you to monitor every endpoint, not just access point. By monitoring every endpoint, you know exactly what sort of performance and connectivity a particular device is getting. And if you have the machine learning models, they can start using that data to do self-diagnosis. For example, simple thing without using too much machine learning, you can detect that the performance is not there, a connectivity issue is there, and you can proactively remediate. For example, for flushing the DHCP cache or restarting a DHCP server or DNS cache and so on. So that's another thing that's happening, which requires you to send data from the endpoint devices access points to the cloud. You can't do that in every enterprise environment, very expensive. So people are using public cloud or data centers, which are at the edge of the cloud. And then, of course, people are developing infrastructure for 5G to really meet the demands of this 1.8 gigabits per second kind of connectivity. And that is enabling new applications. So across enterprise, government, as well as consumer segments, you see these applications coming in. The reason I'm bringing that up to your attention is because that's a data growth we're talking about. But all of this requires some sort of data transfer across the network. either within the enterprise data center or to the public cloud data centers or edge data centers that might be serviced by AT&T, Verizon kind of things. And if you look at the amount of data created, it's as if we haven't seen anything yet, right? Because you see 2020 to 2025, the growth is almost 4x. And the curve really keeps on going up exponential beyond that. So this is not going to go away. A lot of the effort has been on computation and how to make it power efficient. But really the data processing, ML AI based data stores, data lakes, and data processing is likely to take a lot more energy. And that's where the energy efficiency challenges are shifting from the traditional data center architectures, which focused on making data centers energy efficient from computation point of view. So I think the good news here is that, of course, even if the amount of computing has quintupled, the amount of energy usage has not gone up. That's because people have focused on innovations in architecture, transmission, energy conversion, cooling technologies and whole. So a whole bunch of those improvements are definitely working, right? They have really reduced the growth in energy usage compared to the massive computational increase. And that's where my point I'll make in the, I'm on a panel later on where we hope to discuss it. I think, what does the ML AI based processing and data processing mean for energy efficiency? Okay, that's going to be the next challenge in my opinion. So I'm going to talk about in three areas: networks, interfaces, and architecture. And what does that mean from energy efficiency point of view, right? So to start with, I think, let's start with the networking. So I think if you look at the data center designs today, people have made lots of progress with respect to identifying novel ways of getting energy sources as well as novel ways of delivering energy, right? So people use climate-friendly locations. If you're in Pacific Northwest, that's a popular location for locating data centers, right? Facebook has data center there, Google has, Amazon has. Reason for that is the climate there, dry air, helps you to do more and more air-based cooling rather than water-chilled or chilled air cooling, reduces the energy usage for data centers. There are also areas which are really ripe for renewable carbon neutral sources. So in Iceland, they built a large data center, which is completely carbon neutral because it uses geothermal energy as well as hydroelectric sources of energy. But unfortunately, you cannot always choose a location where you can locate a data center. The reason for that is more and more applications that I mentioned, such as augmented reality or IoT, billions of IoT devices. At home, we have 10 to 20 devices now. All of them need to be serviced at the edge of the network for latency reasons, to reduce the cost of data transfer all the way to public cloud. People are building edge clouds. That means they're building data centers in central offices of the service providers or somewhere closer to the customers, which are enterprises mostly. And that means you continue to innovate in energy efficiency. So for example, when you build a data center, people want to use pods with free air cooling or direct expansion cooling. So you do not have to use very expensive chilled air cooling or water-based cooling, right? That's another area that it continues to evolve and it's going to become more important as ML AI becomes important. Because, you know, there are applications like smart manufacturing, smart retail. So I once did a POC, a pilot at VMware with Tesla, where we had Tesla manufacturing has a whole bunch of robots. They need to be controlled and they need to be controlled with a certain low latency. So we were trying to provide an IoT-based edge cloud, which could provide low latency control loop for controlling robots and providing diagnostics and so on. Similarly, smart retail, when retail stores want to keep track of the foot traffic, heat maps in the stores in terms of who comes, who goes, or inventory control, or find that somebody is looking at one particular product, that means they might be interested. You want to get their behavioral analysis and immediately start sending them some rebate coupon while they're in the store. Those applications require you to invest in edge clouds, and which means they're closer to those things because of latency requirement, bandwidth requirement, and to avoid sending all the data all the way back to the public cloud. So that's where I think these technologies are more important in terms of being able to build energy efficient data centers. Switching from AC to DC has two advantages. First of all, it removes lots of conversion steps, reducing losses. That means you improve energy efficiency. And secondly, once you reduce the amount of power, it is estimated that about 15% savings you can get by using DC power versus AC. Less 15% power also means less air conditioning. So you also save energy in air conditioning system. In terms of all the systems that are used in power and cooling systems, you don't have to change the components, but you can upgrade them. For example, one of the simple idea is to use variable speed drives in motors and fans. So you can run the speed of the motor or the fan based on actual energy usage than running at a fixed speed. And that leads to lots of energy efficiency. And that was, by the way, those sort of technologies are not yet widely deployed because every hyperscaler or public cloud provider thinks that's their intellectual property, so they tend to invest in it, right? One of the things that could happen here is that if you remember Facebook's Open Compute project, where they made their server design completely public, including blueprints, mechanical designs, so that the Chinese and Taiwanese ODMs can enter the market, providing very cost efficient but very good designs. That has really flourished right now, right? And that allowed them to also ODMs to start innovating in the area. One of the innovations that was originally there was fan design. How to design a fan just by changing the shape of the blades of the fans. People showed that they can be energy efficient. Variable speed also helps. So there are opportunities for still innovation in this area in terms of both novel energy sources but delivery of energy. The other is finding efficiency in IO interconnects, because IO interconnects takes a lot of energy, right? If you look at and optical networks, the concept has been around for quite some time, right? It started really in early 90s with AT&T trying to build the first optical network and so on. But what is more important is that energy needed for data transport is significantly bigger than energy required for compute. And we have had lots of focus on making computation energy efficient. Companies like ARM and Intel have invested a lot to create energy efficient processors and IO fabrics and memory interconnect, but that's not enough, because a single floating point operation here, it shows 0.1 picojoules per bit. But to be able to take that same data that's involved in floating point operation across just the PCB distance is about 200 times higher. And if you have to, of course, transfer data in a typical data center where people are using disaggregated compute and storage architectures for achieving more efficiency of utilization, you're sending lots of data around, and that's much more expensive, right? Now, one simple example is that if you look at the average power consumption from a 10 gig per second copper file, that's around 300 watts per gigabit. And that's the traditional technology used for interconnects, very popular, right? And we're using active copper link with power control. People have brought it down. People continue to innovate in that. There's a lot of effort in that area. Comparatively, of course, a fiber optic in a transceiver is a lot more efficient, energy efficient, right? And we still are in the process of building optical networks where end-to-end, we do not have to do electro-optical convergence necessarily and so on. But I think more and more energy efficiency is found by investing in IO interconnects. The second area is interfaces. So as I said, optics are the way to go. So data center optics, today, most of the focus has been on the direct detect optics, right? Where, you know, up to 2 kilometers, you can go over unamplified links. Most of the technology is NRZ based modulation. PAM4 has evolved up to 100 gig and maybe even 400 gig using multiple optical lanes at low speed. And in parallel, you have coherent optics. Coherent optics is used today for large distances, data center interconnects. You can go up to 80 kilometers or so, right? Using DWDM links. A very different kind of modulation. Now for 800 gig, more and more it's QAM based on different number of lanes and so on. So those are the two opportunities where there are parallel efforts to improve energy efficiency. And I believe that the coherent optics is providing an inflection point, not just long distances, but even shorter distances. So this graph tries to really show two things, right? It shows how the technology has evolved, right? With QSPF, with respect to direct detect optics, it's climbing in power. Right-hand side, the graph shows the amount of power that's consumed. And coherent optics, on the other hand, and this is adjusted for efficiency losses that you have over longer distances for coherent optics, is definitely constantly coming down in amount of power needed. So I do believe that we are coming to an inflection point where people might consider completely switching over to coherent optics, even for short distances, not just long distance, which is the given. So that's another opportunity that's coming up, especially as we go beyond 400 gig to 800 gig and 1.6 terabits per second and so on. So that's another thing that's definitely very relevant to what work happens at UCSB, in my opinion, and some of the work my team is doing at Juniper Networks, and including lots of ecosystem players. So I think if you look at the concept of pluggable optics, and that's attractive for many reasons, right? And that, as I said, direct detect optics is improving power efficiency, constant improvement, right? It's not necessarily Moore's law kind of improvement, but there's constant improvement. Coherent optics happens to be improving faster in power efficiency, right? And there's also an advantage of using DSPs, where as you go to lower and lower geometries in semiconductor process, you get even better power efficiency with DSPs, right? At greater than 10 kilometers, there should no doubt coherent is a lot more efficient as you go to 1.6 terabits. But there might have been opportunities to try to bring it down and replace direct detect optics in this particular area. Especially when you transition from 100 gig to 400 gig, right? We are already seeing the need to adapt the DSPs to cope with limitations of NRZ modulation and so on. But if you look at 400 gig coherent technology, initially it was deployed for longer distances, right? That really is going to represent sort of I won't say end of the limitation of direct detect optics technology and coherent optics taking over. So truly, I do believe that both the camps will continue to evolve, continue to bring more energy efficiency, but there seems to be an opportunity to identify an inflection point at a right place. Finally, in the area of architecture, here I could talk a lot about, because this is my area of a bigger expertise, I think. I'm going to only talk about co-packaged optics, because I think co-packaged switch silicon electro-optical engine, bringing them together in a single package, that is going to increase a lot. Microsoft and Facebook have already announced a joint effort to set the industry standard towards the 51.2 terabits per second architecture, right, to meet increasing bandwidth data needs. Intel already shown something at 12.8 or something, but with a roadmap to 51.2, so they will have a co-packaged optics. So I think definitely, and there are a bunch of startups in this area which are also innovating in this area. So I think last year's ONF, IFC, if you look at, has set very good 2 milestones, really, which will allow us to make sure that the co-package solutions get adopted. One is the trial of 25 terabit co-packaged Ethernet switch systems will happen in 3-4 years, and also deployment of 51 terabits per second co-packaged Ethernet system by 2026. Within cost, but if hyperscalers are behind it, I do believe that it's likely to happen. And there's a lot of acceleration of this innovation in this space happening. Why is that important? Because if when you go from discrete to co-packaged optics, this shows how the power consumption goes down, right? You typically have switches and optics separated with retimers. There are traces on the board. There are flyover copper cable. They all contribute to amount of power taken. Once you go to switch optics and cables together, where you are bringing optics closer and removing the retimers, that improves the energy efficiency. Co-packaged optics combines everything in a single package, removing all of these tracers, retimers and all. And you can see at the bottom, amount of improvement from first column to last one is almost 50%. Right? 33% rather. That's a huge energy efficiency. So that's another thing that's happening very rapidly in the industry. Standards are still developing, and that's one of the bottlenecks probably, because people have to agree upon that. But Microsoft and Facebook are likely to lead the charge here. With that, I want to thank you for listening.